it not necessarily be true in buildings that probably once a year they see a strong wind. And if the building moves, what's the problem? You know, if you explain to the users that if there is a strong wind, it will move a little bit, okay. If you are in Chicago, that's not the case, because in Chicago, the wind blows strongly one day and the other day again. So that's why it's the windy city. Then you are concerned about this peak acceleration, but not in a building that probably sees once a year. So the structure is very simple. We have these outriggers that's mainly walls, concrete walls only, and a core. So that's what we call an indirect outrigger, because it doesn't go from the core directly to the columns. It goes through this belt, this perimeter belt. And see how effective it is? You know, you can see where you have the two outriggers. So this is the drift and goes back and then goes back. So it controls the drift through the height. So that's mainly the system. And that's it. This is the structure. And you can see some photographs of the building. Very simple, very economical. This was in the time, 8 years ago, $400 square meter of cost. So imagine that. It was like 20% more than a 30-story building, this being more than double, 69 stories. So that's what we want. Now, the influence of the outriggers, they were 25 in the north-south direction, 15% in the east-west direction. So mainly was the core that gave the lateral stability. And the core is defined by what? By the elevators, by the vertical transportation, not by the structure. So when they define the size, it's very easy. We use that as a lateral system. So here is a standard wind tunnel test that we do. And this is what we get. And if you can see, if you think that it was conservative, the design, it was not. It was barely passed. Barely passed. So it was not conservative. It was just calculate what it needed. In December 14, 2018, they have, actually the owner put this a meteorologic station to measure wind. And it happens that that day we have 70% from the wind design speed. So 70%, so it was strong enough. And then, can you play this, this video? No. Excuse me, can you make a play there? Okay, you have to touch that. Okay, so these are in the last floor, the owner's office. And you can see, can you run it again? Can you see the statues that they are hanging at the top? And by the way, who recorded this was the owner, because I told him that in a strong wind, it will move. Nobody noticed about that wind, and this was 70%. So now we try to instrument this building to see really, what are the forces, and use that for the new designs. So that's the beauty of that. And you can see some of the construction of this building that we really took a lot of monitoring, a lot of instrumentation, because this was the first building in concrete and that high. So we wanted to understand. So that's why we were very close with the concrete producer to find out the concrete properties that they are going to provide us. So they sent to us all the properties, detailed properties, the modulus of elasticity that they measure in the lab. They also gave us the creep that they also measure in the lab. So that was beautiful. We did it with different softwares to estimate the long-term effects. Okay, so we did all what we wanted, we could do. So the important facts about the creep and shrinkage are the lateral displacement due to gravity loads, the differential settlement between core and perimeter walls, and the additional forces during time of critical elements. So that's very important in tall buildings. So this is the model, and we did a lot of creep and shrinkage, calculate everything. Everything looks perfect. The modulus of elasticity that according to all the testing in the lab. Then we run the construction sequence. If we go faster, the long-term effects are higher. And that's what we want. So that's contrary to the calculations, because as fast as we go, we have much higher long-term effects. And we have to do at the end of the construction, and then after, you can do 30 years, that's the standard, but, probably most of it happens in the first 5 years. So here's the link beams in the walls that also they varied the forces. So we estimated that the lateral displacement is going to be 13 millimeters in the north-south and 90 millimeters in the east-west. This was mostly symmetric, and this was, like you have the setback at the level 22, you have some eccentricity, so that's why we have 90. And the elevators we designed with the gap of 200 millimeters, just in case. But that's not enough, because if it started for a long-term directions to go in one way, you will start to have problems. So you have to know immediately if we have that problem to correct during construction. So during construction, we can construct the other way. But if it's finished the building, there is no way. Ask the owner of the San Francisco building that was the foundation. It's tilting. Now it's a big problems that they have there because of that. So then we estimate the vertical deformation, 46 millimeters at the construction, the final construction phase, and 160 millimeters of 30 years, because also as a vertical deformation, the columns deform much faster than the core, because you have more stresses in the columns than in the walls. So with that, the floors can have, differential settlement and have problems with the finishings, with the dogs, and everything. So CEMEX, the lab of CEMEX, decided to instrument, because they were worrying about, what will be the behavior of this building. So they put instruments in these 4 columns that are in colors. So here, the red, the green, the black, and the blue. You can see the setup of the instrumentation. And you have to know the dates that you are measuring. Here are the concrete strengths of the concrete during the different time, 28 days, 56 days, and 91 days. The concrete was specified 91 days, not 28. 28 doesn't mean anything for the tall buildings. Because what's the need of having in 28 days the concrete strength? There is no use because you have a lot of floors above. So usually we specify for 91 days. So the 70 70 megapascals was not achieved. This was 700 kilograms or 70 megapascals, and it was not achieved in 28 days, but it was at 56 days. And like I say, we have a lot of data of this building. If you want to measure the modulus of elasticity, here's the code. The black one is ACI, high-strength concrete, ACI. This is our code. All the data is above that. All the data. So can you say that the code really predicts the behavior of the building? I will say not even close. And here are the measurements. 3,000 days. And this was, I will say, measured before my trip. It was September 8th, but they gave me like 2 days before I depart from Mexico. And I asked, I request the information. See, during construction, it goes very, very rapidly, this long-term deformation. But after that, it continues, but it started to slowly decrease until it will not shrink anymore. But after 3,000, so we monitor in the -5 at the basement, 27 and 52 level. Now, the result of this monitoring was that the long-term deformation were less than 1/2 of what the lab said to us, which is really fantastic. In the future buildings, we don't need to worry about this. We can calculate out of that. Only be precaution that will be the same concrete. You cannot take this to your building and say, oh, it's 50%. We are not going to worry. No, be careful. We have to make sure that it's the same production, the same aggregate, the same admixtures, or everything the same in order to do this. But these things can be rapidly adjusted nowadays with our software. If we see these measurements, we can adjust, and we can even reduce some of the steel or of the sections of many things. We can adjust and have a more efficient building. And that's the important part of this monitoring idea. And later on, we can monitor many things, because sometimes we try to evaluate certain values, certain parameters, which is impossible, like the soil structure interaction that I gave the task to Professor Nelson. It will be a challenge to do soil structure interaction. Every time that I ask people in these large offices like Thornton Tomasetti, WSP, or others, oh, what do you opinion about the soil structure interaction? They say, oh, it's a difficult task. Some of them, they say it's impossible to evaluate. So if we can monitor our structures, immediately we can have a much better understanding. And cracking is the other thing. Concrete cracks. How much it cracks? Who knows? And for wind, sometimes they use the concrete properties that we use for earthquakes. Doesn't mean anything. Crack, you put the flexural stiffness of a beam 35%. But in wind, probably it's 80%. So you are not taking advantage of this data, this very valuable data. So with this in mind, I conclude. Obrigado, and I'm ready for questions.
Bom, muito obrigado, Roberto. Se alguém tiver alguma pergunta, a gente pode passar aqui para as questões. Alguém? Professor?
Parabéns, Roberto, pela apresentação. Muito... Não está prestando atenção em mim.
Não sei se... Okay.
Parabéns pela apresentação, muito didática e interessante, situando bem a questão dos edifícios altos. Perdão. Eu tenho curiosidade para saber como é que você especifica o módulo de elasticidade, porque tem um da STM que é diferente do módulo de elasticidade do método brasileiro. Poderia, por favor, falar um pouco sobre isso?
Yes, a very good question, Paulo. I think it's, I will say, most of the formulas that they use, it's very difficult, like we have seen, to predict the modulus of elasticity. So basically what we use is the number, not the formula. So if they, instead of giving, 14,000 square root of F prime sub C, we ask the concrete producer, what are your values? And that's, thank you. And this is what we start, the point that we start. After that, we measure in the field.
Fazer perguntas? Uma pergunta aqui.
Bom dia. Eu tenho uma curiosidade. Qual é o custo de instrumentar uma estrutura dessas comparado com o custo da estrutura? Meu nome é Fernanda, eu trabalho no Instituto de Pesquisas Tecnológicas do Estado de São Paulo.
Yes, also very good question. And I thought that someone will ask me that question. So for the BBA project and the other building, so far we have 3 buildings instrumented, and we are about to start the 4th one. The 4th one is in a city 2 hours away from Mexico City that also is a high seismic zone. So the full instrumentation with the nonlinear model and with the instruments inside costs about $130,000. And that's it. And that's the cost of the instruments, the maintenance, the interpretation, everything, $130,000, which is nothing for a building that cost in that time, when it was constructed, $350 million. So that's peanuts, what we call. Yes.
Muito bem. Mais ninguém? Mais uma pergunta.
Tudo bem, professor? Me chamo André. Eu gostaria de saber se no Brasil o senhor tem algum trabalho de instrumentação similar ao que o senhor apresentou aqui. ou se é possível fazer também um trabalho desse aqui no Brasil.
Yes, I will say yes, it's very simple to put it, and I'm sure that it can be done here. Of course, it will not work for seismic, it will be for wind and for concrete properties, yes. It's very easy and very inexpensive nowadays.
Bom dia, professor Roberto. Parabéns aí pela apresentação. Meu nome é Jean Penha, sou engenheiro civil. Quais são os estudos, né, para o efeito sísmico voltado para as empresas de data center no México? Uma vez que a internet 5G, enfim, não pode ter interrupções, né, na fase de alimentação energética, né, não pode parar. Né? A gente tem acompanhado, né, alguns estudos voltados a esse trabalho, a preocupação do efeito sísmico, né, e sabemos que empresas de data center ela consomem muita energia, né, e numa situação dessa de sísmica, enfim, isso tem algum estudo em paralelo sendo feito?
Well, I'm not the seismic guy, so that's difficult to answer in that respect about this energy and all that. But yes, we have an institute that is dealing with all this data that can be. But some of this instrumentation helps you indirectly to measure these things. So that's the good part out of this. This is a very practical. Actually, you know, when I had the idea and I said to the Spanish directors about this idea, I didn't have a clue of what I was entering. So I called my advisor at the University of Illinois, Mette Sonsen, and say, Mette, I'm in a big problem. Can you help me? So basically, he helped me to find how to instrument the building. And at the beginning, he said, well, you know, in the lab, we will put 256 instruments. I don't know how he derived to that number, honestly. But he said, oh, we have to be realistic. And he was very, very realistic guy, very practical guy. And he said, I will say let's put 8 instruments. Nowadays, there is in the California environment, or in California, they are now saying that if you have 50-story building, which is the case, you need at minimum 8 instruments. So he was right, as always, you know? And we put 8, but you can put 6 and you get the same answer. As more as we have, it will be better data and better calibration with your model, but it not necessarily be as many as 8 instruments. If it will be taller, you will certainly need more instrumentation. But you get a lot of properties indirectly, but at the end, as a structural engineers, you don't need to know every single item separately, like soil structure interaction. You don't know, you know, how much damping gives you the soil or the structure or the basements. Who cares? What I need is the base, the ground motions at the base and at the top, because then you can know the amplification that you get inside the building. And it's very different. We found that it's really very different for all the tools that we had so far. You know, whatever you predict is wrong. That's what we learned from the instrumentation. And that's the beauty of having all this data. Actually, we are designing a building that is next to this one. It will be a 305 meters tall. We are using the ground motions from this building, not what it says the code, not what it says from the sites spectrum of site studies. We are using from our building because we have the correct data. So that's now the other building, we are designing 50% less forces, and the government accepted because it's a proof that acceleration are not as high as we can get from the code.
Bom dia, professor Roberto. Parabéns pela apresentação. Adriana, da IDTEC. Grande problema que nós temos aqui na nossa engenharia nacional é que muitas das instrumentações, às vezes, que são pensadas e são instaladas durante a construção, na hora que troca as equipes, né, isso sai da mão do construtor e vai para a mão do proprietário, nós temos muitos problemas de manutenção dessa instrumentação, né, e de se manter a frequência correta, as leituras, até a análise desses dados. E aí, no seu caso, né, como essa instrumentação ela influencia até na segurança, né, do edifício, né, no caso de terremotos, como que foi esse processo de fazer o proprietário do prédio manter, né, todo esse processo de instrumentação e monitoramento da estrutura? Assim, que cuidado que teve que ter nessa transferência entre o construtor e depois o proprietário?
Yes. Yes. Well, I have been lucky that the owners really, first of all, it's one owner. It's not, like in a condominium that they have 100 or whatever. In these buildings, probably you will have over 800 owners. No, the thing is that in the 4 buildings that we instrumented, we are directly with the owner or with the institution. So they maintain the instrumentation there. Actually, the first contract for the instruments was only 4 years. They decided to have it permanently. So, and that's very smart because, the maintenance of those instruments are very low. If I told 130,000, annually they pay 20,000 to maintain the instrumentation. For this building, for $350 million building, it's nothing. And the other Torre Coy, the one in Monterrey for the concrete properties, they maintain. I was even surprised because I thought that in the -5, in the parking, okay, that's very easy to maintain the instrumentation. But in 1127 or 52, it's a residential part. And still the owner accepted that they will go and measure this. So I think it's a very easy to convince, but if you have one owner. I agree that if they have different or they don't have an administrative out of the condominiums, it will be very, very difficult sometimes because, one can say, no, I don't want to keep the instrumentation, and that's enough because he's the owner. So you have to convince, and I think if you showed all this data and the beauty of monitoring buildings, I think everybody will accept. The problem is that it's new and they don't know about this. But if we start to publish these ideas, I'm sure that every day they will start convincing that this is the way to go. Because some of these theories, like we saw, they are not applicable. So that's the beauty of doing this. Okay.
Muito obrigado, Roberto. Excepcional palestra. Muchas gracias. Thank you. Uma salva de palmas, por favor. Roberto Stark. Vou convidar agora aqui o engenheiro Sérgio Stolovas para a segunda apresentação. Se puder, por favor, trocar a apresentação para aquela primeira. Sérgio Stolovas, da STO Análise e Soluções Estruturais, engenheiro civil, especializado em dinâmica estrutural, engenharia sismo-resistente e análise de efeitos dinâmicos, oriundos aí ações humanas, máquinas. Desde 85, participa de projetos na América do Sul. América do Sul, Centro-América, Inglaterra e Oriente Médio, né?